level 33, we're going to start talking about the quantum mechanical model of the atom, which is our current and most modern model of our atom. So when Bohr's model could not work, three other physicists began working towards a new model: Heisenberg, de Broglie, and Schrödinger. The approach they developed became known as wave mechanics, or more commonly, quantum mechanics. For more of their development, for more information about what they did, see pages 310 to 313 in your textbook. We don't really need to get into the calculus and all of that kind of thing that they use to solve this information, but it is there in your textbook if you're really interested. This equation that Schrödinger developed for the hydrogen atom had many wave functions that satisfied it. Each of these orbitals is characterized by a series of numbers called quantum numbers, which describe various properties of the orbital. For more information about quantum numbers in your textbook, refer to pages 313 to 317. The College Board does not need you to identify quantum numbers per se, so we will not have to actually assign quantum numbers on the AP exam, so this is not going to be as in-depth as it was in Chem 1. The principal quantum number is the first one, and we signify that by the letter N, and this tells us the energy level. So when we were talking about Bohr's model, we had N equals 1 equals 2, we were talking about the energy level. So it's the size or volume of the space, which we call an atomic orbital, in which the electron moves. So N can be a whole number beginning with 1, and it currently ends with 7 because there are 7 rows on the periodic table. As N gets larger, the energy associated with the energy level increases, and the average distance from the nucleus for the electron also increases. The next quantum number is the secondary quantum number, also known as the angular momentum quantum number. This designates the shape and the region in which the electron occupies. We use a cursive L, lowercase l, to signify this. Values of L are whole numbers that start with 0 and go up to the quantity n minus 1. We have specific sublevels that are associated with the values for L, S, P, D, F, and there are pictures in your textbook of these shapes, which I'm going to show quickly here. But the reason why I'm including the SPDF is because we're going to need to know this for electron configuration. And we also need to know for electron configuration in level 34 that each sublevel can hold a maximum number of electrons. So S can hold 2 electrons, P can hold 6, D can hold 10, and F can hold 14. Again, all of this should be review from Chem 1. The next quantum number is M, the magnetic quantum number, and this tells us the orientation of the electron path around the axis or axes in which the path is oriented. So it's like where the Earth is orbiting around the Sun at a given time. The values of M are whole numbers that vary from negative L up through positive L. And then last but not least, but one of the most important, is the spin quantum number S. And this tells us that the spin of the electron, if it's going clockwise or counterclockwise. So we can denote that by positive or negative halves or up and down arrows. Because of the 2 directions of spin, each magnetic number will have 2 options too. So the spin is what's telling us that orbitals can hold at maximum 2 electrons, which is important in level 34. The Pauli exclusion principle is the main significance of the electron spin, where Pauli came up with, in a given atom, no 2 electrons can have the same set of 4 quantum numbers: the N, the M, the L, the M, and the S. So an orbital can only hold 2 electrons, and they must have opposite spins when that orbital is filled, which we will, in level 34, go over an orbital diagram very quickly, just to show you how there's only 2 electrons that can be fit in there. We also have polyelectronic atoms. The quantum mechanical model gives a description of the hydrogen atom that agrees very well with experimental data. However, it would not be very useful if it didn't account for the properties of all the other atoms as well. So, when electrons are placed in a particular quantum level, they prefer the orbital in order of S, P, D, and then F, which this is kind of signified by the periodic table. So the history of the periodic table: our modern periodic table contains a tremendous amount of useful information, from the numbers that are in the boxes to the arrangement of it, all that kind of stuff. It was originally constructed to represent the patterns observed in the chemical properties of the elements, before they really knew about electrons and what the electrons can do. So the present form of the periodic table was independently conceived by two different people, but it's mostly given credit for Mendeleev, because he was the one who emphasized how useful the table is in predicting the existence and properties of still unknown elements, which he was able to predict the elements like gallium and scandium and germanium, all of which were still unknown at the time when he was developing his periodic table. Today we know we have a lot more information on the periodic table than what they knew back then, but this is pretty good for the 1800s, right? So this is a picture of Mendeleev's periodic table and what it would look like. And notice how he was able to predict with the blue boxes those elements that hadn't been found yet. So this is it for level 33. There's no assignment for 33. Please continue to watch 34 so that you can do the 34 worksheet.
We may share